Let's go.
Hello, we are Group B26, and we will be teaching you about mathematical induction.
Suppose we are at the base of an infinite ladder. This ladder has a starting base and goes on infinitely. So we know that we can reach the first rung of the ladder. If we can reach an arbitrary rung of the ladder, then we can reach the next rung. This is known as the inductive step. From this, can we conclude that we can reach every rung?
So here's where mathematical induction comes in. The principle is to prove that P of n is true for all positive integers n, where P of n is a propositional statement or function. And we can complete this in two steps. The basis step is where we verify that a certain base case of P of n is true. We denote this P of n naught. And now this leads us to our inductive step, in which we wish to show that since P of k is true, then P of k plus 1 is true for all positive integers k.
So the format for a mathematically inductive proof is to first express the statement to be proved. Next, you're going to want to state the basis step and show that the base case Pn is true. Next, state the inductive hypothesis in the form assume that pk is true for any arbitrary integer k is greater than or equal to b. Next, write out pk plus 1 and what it implies. Then prove the statement pk plus 1 using the assumption of pk. Then clearly identify and state the conclusion of the inductive step, i.e. Pn is true for all n is greater than or equal to b.
So, moving on to our first example, we wish to show that this inequality, n is less than 2 to the n for all positive integers n, is true. So, n is less than 2 to the n we'll call our P of n, or statement we wish to prove. And our basis step says that we're trying to prove the initial P of n is true. And since 1 is the least positive integer, we wish to show that P of 1 is true. And it is because 1 is less than 2 to the 1, or 2. And so this completes our basis step. Now we move on to our inductive step and say that because P of k is true, now we move on to our inductive step in which we assume P of k is true for an arbitrary positive integer k. And we are trying to prove P of k plus 1. Which is k plus 1 is less than 2 to the k plus 1. So, if we know from our inductive hypothesis that k is less than 2 to the k, then k plus 1 must be less than 2 to the k plus 1. And we know that 1 is less than or equal to 2 to the k for any positive integer k. Now, we know that 2 to the k plus 1 is also 2 times 2 to the k. So, we know that this part is less than 2 to the k, and this part is also less than 2 to the k. So their sum cannot be more than 2 times 2 to the k. And this proves that the left side is less than the right side. So, this shows that P of k plus 1 is true, namely this statement right here, and the inductive step is complete. Therefore, by the principle of mathematical induction, we have shown that n is less than 2 to the n for any positive integer n.
Alright, this brings us to example 2. So, say we have the sets A1 through AN and B. Then we want to show that the intersection of the sets A1 through AN, union B, is equal to the union of the intersections of the individual sets AI and B. So for all n greater than or equal to 1, Pn is true. where Pn just denotes this statement up here. So the basis step is P of 1, which says that the set A1 intersection B is equal to A1 intersection B, which is true. So for the inductive step, we assume that P of k is true for an arbitrary fixed integer k is greater than or equal to 1. Then we want to prove that the union of the sets A1 through AK plus 1 intersection B is equal to the union of the intersections of the sets A1 through AK plus 1 and B. So first, we'll show that the union of the sets A1 through AK plus 1 intersection B is equal to the union of the sets A1 through AK union AK plus 1 intersection B. This equals A1, the union of the sets A1 through AK intersection B union AK plus 1 intersection B. So this equals the union of the intersections of the sets A1 through AK and B union AK plus 1 intersection B. Finally, this equals the union of the intersections of the sets A1 through AK plus 1 and B. So this completes the inductive step. And by mathematical induction, P of n is true for all integers n with n greater than or equal to 1.
So for our third example, we need to prove that n squared minus 7n plus 12 is non-negative whenever n is an integer greater than or equal to 3. So for our basis step, when n equals 3, then 3 squared minus 7 times 3 plus 12 is 0, which is non-negative. Now for an inductive step, we assume that P of n is true. Then P of n plus 1 equals P of n squared minus 7 times n plus 1 plus 12, which then simplifies to n squared plus 2n plus 1 minus 7n minus 7 plus 12, which then simplifies to n squared minus 5n plus 6, which is greater than P of n, which is n squared minus 7n plus 12. Since P of n is non-negative and P of n plus 1 is greater than P of n, P of n plus 1 must also be non-negative. And now for our last example, we will prove that n squared minus 1 is divisible by 8 whenever n is an odd positive integer. So for our basis step, we'll let n equal 1. Then 1 squared minus 1 equals 0, which is divisible by 8. For an inductive step, we assume that n squared minus 1 is divisible by 8, provided that n is an odd positive integer. And then we have n squared plus 2, because n needs to be an odd number, n plus 2 squared minus 1 equals n squared plus 4n plus 4 minus 1. Since n squared minus 1 is divisible by 8, and 4n plus 4 simplifies to 8n plus 8 times n plus 1 over 2. And since both of these are divisible by 8, when you add them together, then they are also divisible by 8. And that is mathematical induction.
All right.
Voila.
Thanks for listening.